As promised, we're going to develop better and better ways to compute the value of Legendre symbols. In this video, we're going to prove something called Gauss's method, although we are going to postpone working out examples. The proof takes long enough on its own. So here's the statement of the theorem. Suppose P is an odd prime and A is relatively prime to it. N is going to count 1, 2, 3, 4, and so forth, all the way up to P minus 1 over 2. F of N either spits out a 1 or a 0, according to whether the remainder of n times a over p is bigger than p minus 1 over 2 or less than or equal to it. So as n counts 1, 2, 3, 4, and so forth up to p minus 1 over 2, you compute the multiples of a and ask, is the remainder bigger than this or less than or equal to it? Accordingly, you spit out a bunch of 1s and 0s. Then let g of a be the sum of all of those. Then Gauss's method is that the Legendre symbol a over p can be computed as -1 to that power. So it takes a few steps to execute, and it's going to take many steps to prove. We will see in the next video, once we finally finish the proof of this, the next video will be applying it and doing examples. We'll actually see that it is a tremendous improvement over Euler's method. Okay, it does take some time getting used to it, okay, but it will be a better way to compute Legendre symbols once we finally get our hands around it. So let's discuss the formula and do one sample computation just to understand what these terms actually represent. We haven't actually proved Gauss's method works yet, but we're going to apply it to the Legendre symbol 7 by 31. So what we're going to have to do, phi of 31 over 2, is 30 over 2 is 15. So as n goes from 1 to 15, we compute multiples of 7. So 7, 14, 21, 28, and so forth, all the way up to 7 times 15. We compute the remainder when we attempt to divide by 31, and we ask how many of them are bigger than p minus 1 over 2 and how many of them are less than or equal to it. If I add up all of these ones, what I'm really doing is counting how many of them were bigger than p minus 1 over 2. That's what g of a is. Then I take -1 to that power. Okay, so what's the function f do? We compute the integer n times a. That's just multiplication, and then we find a remainder. The value is somewhere in between 0 and p minus 1, because the remainder has to be. If the remainder is bigger than p minus 1 over 2, we count a 1, and if it's less than or equal to it, we count a 0. So for 7 and 31, we compute all the multiples of 7 up to 7 times 15. So in theory, what you're doing is multiplication. You're doing 7 times n. But if you're doing this iteratively, what you're really doing is adding 7. Here's a multiple of 7. 7. Now add 7 to it. 14. Add 7. 21. So to make this entire list, don't think of it as doing multiplication. Think of it as doing a bunch of addition. 7 plus 7 is 14, plus 7 is 21, and so forth, until you get out to the 15th multiple in this list. Also, we're only interested in the remainder under division by 31, so let's reduce it mod 31 as we go. So 7, 14, 21, 28, I'm just adding 7 every time, and I haven't reached 31. But now what happens? I reach 35. But 35 modulo 31 is equivalent to 4. So 4 is 7 times 5. How do I get from 7 times 5 to 7 times 6? All I have to do is add 7. So don't think of this as 7 times 6 is 42, and then reduce mod 31. Think of it in terms of, I already know 35 is equivalent to 4. So to add 7 to 35 is the same thing as adding 7 to 4, and that's easy. So 7 times 7, just add another 7, 18. 7 times 8, add another 7, 25. Now 7 times 9 would actually be equivalent to 32, which is equivalent to 1. 7 times 10, add 7. 7 times 11, add 7 to what you had before. 7 times 12, and so forth. So ultimately, we end up with the following list of all of the multiples of 7 up to the 15th one. I count this out by saying I put 4 here, 4 here, 5 here, and then I only need 2 more here. So what we have now is a list of 7 times 1 through 7 times 15, all reduced modulo 31. Which of them are larger than p minus 1 over 2? Which are larger than 15? F of those would be 1, and f of anything else is going to be 0. So, too small, 0. Too small, 0. Big enough, 1. Big enough, 1. 0, 0, 1, 1. Small, small, big, big. 0, 0, 1, 1. Small, small, 15 is equal to 15, which is too small. And then big, big, so small, 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 big, big. And then both of these are less than or equal to 15, so zeros. So here are my values of f. I went through this list and I said, if it is less than or equal to 15, give it a value of 0. If it is strictly bigger than 15, give it a value of 1. So then all we have to do is add up that list. The individual terms in the list were either 0 or 1, so really what you're doing is counting how many times did I get 1. So put succinctly, in the list that we generated, compute the remainder and just count how many have remainders larger than p minus 1 over 2. In our previous example, we computed remainders and we got the following list. This contains exactly 6 terms larger than 15. 1, 2, 3, 4, 5, 6. Therefore, there were 6 terms larger than 15. So our exponent is 6, and we compute negative 1 to the 6th, which is 1. So 7 is a quadratic residue modulo 31 according to this technique. Now what we didn't have to do was apply Euler's method and compute 7 to the 15th. Let's be a little more explicit in our comparison to Euler's method. Euler's method says compute a to the p minus 1 over 2 modulo p. Brute force is to just multiply a against itself, p minus 1 over 2 times, and every time you do that, apply the division algorithm to get the remainder mod p. So we have p minus 1 over 2 steps of multiplication with the division algorithm. If you are familiar with the successive squaring algorithm, that actually speeds it up a bit to a logarithm of p minus 1 steps of multiplication, plus a couple of others, but essentially it's log of p minus 1 that's really controlling how long it takes. But the multiplication can still be fairly tedious, especially when the base is large. Gauss's method, however, says list out all of these multiples. That doesn't actually require multiplication. What it requires is a bunch of steps of addition. To get from a to 2a, just add a. To get from 2a to 3a, just add a. So you're not actually multiplying at all, you are adding. So if I compare the brute force versions, instead of doing a whole bunch of multiplication, we're doing a whole bunch of addition, and addition is usually a lot easier to do than multiplication. Okay, now we're going to proceed to proving that Gauss's method works. It's going to take some time. We start off with what we call a lemma, a preliminary result. Suppose p is an odd prime, and it's relatively prime to a. Let S be the set given by the first p minus 1 over 2 multiples of a. So a times 1, a times 2, up to a times p minus 1 over 2. So here's just a set of values. We're going to do a bunch of things to the set S, and then we're going to make a claim about what we've done. The first thing we do is replace every element with the value from the standard complete residue system. So something between 0 and p minus 1, in other words, the remainder, under division by p. So take your set of multiples and replace them all with the equivalent value from the standard complete residue system mod p. Then take those remainders and write them in increasing order. The remainders probably shuffle around a whole bunch. So put them in order of getting bigger and bigger. And I'm going to present this as a bunch of terms that I call the b terms, followed by a bunch of terms called the c terms. Now these have to be written in increasing order. So the smallest thing in the whole list is b1. B2 is bigger, B3 is bigger, up to BM. C1 is bigger than BM, and then I keep getting bigger. So what's the cutoff to split where I call them B versus where I call them C? The B's are exactly the remainders less than or equal to p minus 1 over 2. The C's are exactly the remainders bigger than p minus 1 over 2. So of all of the possible remainders, I essentially split it into the small remainders and the big remainders. Next, I form the set S double prime. The small remainders I leave alone. The big remainders I replace with p minus whatever they were. So this is now just a different set of values. The small remainders I left the same, the big remainders I changed. I replaced them with p minus what they are. The claim that we're making is that at the end of the day, the set S double prime is simply as a set the values 1 through p minus 1 over 2. Here's overall what we do and what we claim. List out the multiples of A. Replace them with their remainders under division by p. Then I put those in increasing order and I say some of them were smaller, some of them were bigger, determined by the cutoff value of p minus 1 over 2. Anything that was bigger, strictly bigger than that cutoff value, replace with p minus whatever it was. The ones that were less than or equal to p minus 1 over 2, leave unchanged. List out multiples, take remainders. Big remainders get replaced while small remainders are left alone. The claim is that at the end of the day, you are guaranteed to exactly have the list 1, 2, 3, etc. up to p minus 1 over 2. But now we have to prove it. Okay, so let's prove that result. As we go through the proof, to keep things straight with what we're doing, we're going to do a parallel computation of p is 31 and a is 7 to just sort of clarify what's happening. Having an explicit computation done side by side will hopefully make this clearer. Since a and p are relatively prime, and 1 through p minus 1 over 2 are all distinct values mod p, then all of these are all distinct values mod p. Basically, if I continued this list to go all the way up to p minus 1, I'd have a reduced residue system. If I multiply everything by a, that whole thing would still be a reduced residue system, so they'd all be distinct. And this is just some of those values. Okay, so these are all distinct modulo p. For example, if p is 31 and a is 7, I list out 7 times 1 up to 7 times 15. If I reduce these modulo p, they all remain distinct. So here's my set S prime. Reduce all of these modulo 31. 7, 14, 21, 28 remain the same, but 35 mod 31 is 4. 42 mod 31 is 11, and so forth. And notice these are all distinct elements. Now what you do is you list this in increasing order. So I just take a look at the list of values I got, and I go from smallest to biggest. And here I am. So from the set S prime, which are all of these distinct remainders, any that were bigger than p minus 1 over 2, I replace with p minus x. Now, since every element of this is a remainder and therefore smaller than p minus x is also positive, okay? My remainder was less than p, so this remains positive. But since x was assumed to be bigger than p minus 1 over 2, p minus x is lesser than p minus 1 over 2. P minus 1 over 2 is just p plus 1 over 2. So p minus x is strictly smaller than p plus 1 over 2. So p minus x is an integer. If it's bigger than 0, it's less than or equal to, it's bigger than or equal to 1, apologies. But if it was strictly smaller than p minus 1 over 2, then it is less than or equal to that minus 1. Which works out to being that p minus x must be a value in between 1 and p minus 1 over 2. So the small remainders I left unchanged. The things that were bigger than p minus 1 over 2 get changed to be something in between 1 and p minus 1 over 2. S prime had exactly p minus 1 over 2 elements. It was just a bunch of different remainders, and it was exactly this many of them. After this replacement, I'll have my set S double prime. The small values were already between 1 and p minus 1 over 2. What used to be a big value now gets replaced with one of the possible small values. So every element of S double prime is in between 1 and p minus 1 over 2. It has this many numbers, except I may have accidentally duplicated something. One of my previous large values may now overlap with what used to be a small remainder and already existed in the set. If we can show that doesn't happen, in other words, this is a bijection, then there are this many elements, there are this many possible values, so it must contain exactly those possible values. So really what we have to show is that when I take the big remainders and I replace them with p minus them, I don't overlap with a small remainder I already had. In our example, here was our list of remainders S prime. Anything that was bigger than 15 gets replaced with 31 minus that. So 18 is going to be replaced with 13. 21 is going to be replaced with 10. 22 is going to be replaced with 9, and so forth. So as I replace them term by term, I just get this list right here. And if you look at this list, it's exactly the numbers 1 to 15. The big remainders, 18 through 29, got replaced with 31 minus them, starting here, 13, 10, 9, 6, 3, 2. And none of these values overlap with remainders that we already had. That's what we need to show always happens. When you take one of your big remainders and subtract it from p, you don't happen to duplicate a value of a remainder that you already saw. So that's what we need to show always happens. Then this list will have exactly p minus 1 over 2 elements with no duplicates, and they are all less than or equal to p minus 1 over 2, so they will just be that list. All right, so from the set of the small remainders and the big remainders, okay, notice they are listed in increasing order, so b1 is less than b2 and so forth. All of the b's are less than or equal to p minus 1 over 2, and all of the c's are bigger than p minus 1 over 2, but they're never bigger than p minus 1, because they're all remainders when doing division mod p. Replace these with p minus them while leaving these values unchanged. So the b's get left alone, the c's get replaced. The b's are definitely all different from one another because they were all different remainders under division mod p. The c's are all different from each other, therefore the p minus c's are all different from each other. What we just need to show is that one of the small remainders is never the same as one of my modified big remainders. So let's assume that this does happen. One of my small remainders is in fact equivalent to one of my big remainders, modified by doing p minus it. So bi is a small remainder. It's k1 times a mod p. It's equivalent. The c was one of my big remainders, so it's equivalent to k2 times a mod p. And bi is equivalent to p minus cj. So bi, which is just a remainder, is equivalent to p minus a remainder. Okay, well the p is just equivalent to 0, so let's ignore it. Now what we get is that p must be a factor of k1a minus negative k2a, and I can factor an a out of that. Both k1 and k2 were the things that we were multiplying by. The things that we were multiplying by started at 1 and only went up to p minus 1 over 2. From our original list of remainders, we just did a, 2a, 3a, 4a, up to p minus 1 over 2a. So k1 and k2 correspond to multiples of a that we saw. So k1 and k2 have to be in the list from 1 to p minus 1 over 2. These were the only multiples we constructed. So since both of them are in between 1 and p minus 1 over 2, their sum is in between 2 and p minus 1. So p is a factor of k1 plus k2 times a, but it's relatively prime to a. However, since k1 plus k2 is in between 2 and p minus 1, and p is prime, it's also relatively prime to k1 plus k2. But if p is relatively prime to both a and k1 plus k2, it's relatively prime to the product, which contradicts the fact that it is a factor of the product. Therefore, we never have one of our small remainders equivalent to p minus one of our big remainders. Therefore, the elements of S double prime are never equivalent to each other mod p, so they're all distinct values mod p. There are p minus 1 over 2 of them, and they were all in between 1 and p minus 1 over 2, so they must be exactly that list. So we've finally established our first lemma in the proof of Gauss's result, that if you take the multiples of a up to a times 1, a times 2, up to a times p minus 1 over 2, replace them with their remainders mod p, then take the remainders that were larger than p minus 1 over 2 and replace them with p minus that value, you always get exactly the list 1 through p minus 1 over 2. Now we can finally actually prove Gauss's method works. So let p be an odd prime, let a be relatively prime to it, let S be the set of remainders, let n be how many of them are larger than p minus 1 over 2, then we claim the Legendre symbol can be computed as -1 to that quantity. This is equivalent to our formulation earlier. As in the previous lemma, we're going to let s double prime be exactly what it was before. From s prime, replace any element which is larger than p minus 1 over 2 with p minus it. So we've replaced exactly n elements with their negatives, where n, notice, is how many are bigger than p minus 1 over 2. How many of the remainders were sufficiently big? Those are exactly how many get replaced in constructing the set s double prime. So the product of everything in s prime is the same as the product of s double prime with an additional factor of -1 to the n, because I'm replacing x with p minus x. Modulo p, this is just minus x. So how many things in s prime got replaced with their negatives? N of them. So when I multiply everything in s prime versus s double prime, I get the same values, but in s double prime, I have a bunch of negatives. I have n different negatives introduced. So s double prime and s prime are the same product up to this additional factor of -1 to the n. But s double prime by the previous lemma is just the numbers 1 through p minus 1 over 2. So the product is just the factorial. In other words, s double prime is just this factorial when I multiply everything. Here is s prime when I multiply everything together. And the only difference between these two products is this missing factor of -1 to the n. How many terms needed to be replaced with their negatives, n of them. Modulo p, I therefore would say p minus 1 over 2 factorial is equivalent to -1 to the n. This is just equivalent to a. This is equivalent to 2a, all the way up to this is equivalent to p minus 1 over 2 times a. So notice I get a 1 times 2, etc., times p minus 1 over 2. But I also get an a times a and so forth, where I get my a to the p minus 1 over 2. So modulo p minus 1 over 2 factorial is equivalent to -1 to the n times a to the p minus 1 over 2 times this thing here. So here's where we are. P minus 1 over 2 factorial is equivalent to -1 to the n, where n is how many of the remainders when working through various multiples of a were larger than p minus 1 over 2. A to the p minus 1 over 2, and then, hey, this product is just p minus 1 over 2 factorial again. Everything in constructing that factorial, 1, 2, all the way up to p minus 1 over 2, they're all relatively prime to p, because this factorial doesn't go beyond the value of p. So these values are all relatively prime to p, so is this factorial. So if this factorial is relatively prime to p, it has an inverse, and we can just cancel it out. So I get 1 is equivalent to -1 to the n times a to the p minus 1 over 2 mod p. By Euler's method, what's a to the p minus 1 over 2? It's equivalent to the Legendre symbol a over p. Multiply both sides by -1 to the n, and observe that -1 to the n is either +1 or -1, but when I multiply it by itself, I definitely get out a 1. So here we have it. If I multiply both sides by -1 to the n, I get it on the left, I cancel it off on the right, and we get the Legendre symbol a by p is equivalent to -1 raised to the n power, where n is how many of the remainders of a, 2a, 3a, up to p minus 1 over 2 times a are larger than p minus 1 over 2, and that's Gauss's method. So we have finally proved Gauss's method works. We can compute Legendre symbols by listing out multiples of a, reducing them modulo p, and then looking, of those remainders, how many of them are larger than p minus 1 over 2, and raise -1 to that power. That's Gauss's method. This video is already long enough just to prove that it works. In the next video, we'll work through several examples.